So welcome everybody. So today's topic is about superconductivity and superconducting electronics in relation to Ginzburg-Landau theory of phase transitions. And this will be a kind of new type of theory that will be introduced. So this type of theory will result in considerable simplification of mathematical apparatus that is going to be used, and this will be later seen as a phenomenological approach towards superconductivity phenomena. Still, various predictions are possible in this framework of this formalism, and these predictions can be enhanced using more sophisticated formalism, as Bogoliubov-Dijen formalism, which was sketched last week. Okay. So basically, we are having this picture of history of superconductivity discoveries and Nobel Prize winners on the right side. So we were digging in. So last week it was described from 1957, BCS theory, essentially created by Cooper, and then in the whole picture Barton and Schreifer. But this is a mean field theory, BCS theory, but it was not. It produces quite complicated mathematical apparatus that is not always that deeply practical. And today we will talk about theory of nonlinear Schrödinger equation in a way. So this will be Ginzburg-Landau theory. And this is a theory which borrows from Landau phase transition theory. So this phase transition theory is about second order phase transitions. For example, when ferromagnetic behavior can be scaled with temperature. Yeah, so we will talk about this in greater detail. So we are remembering our first technological motivation, and this is about Josephson effect. So we have Josephson junction, which is a system of superconductor, insulator, superconductor. And this system is parameterized by RCSJ model. And this can be described by two-fluid model, which is essentially expressed by equation number 3. Then this whole system can be described by Bogoliubov-Dijen equations, which were sketched last time. So it was like these equations were Yes, please mute yourself. There was one guess, H. Please mute yourself. Okay. Right. So this structure could be described by this phenomenological Hamiltonian, and with in the framework of two-fluid model, or in Bogoliubov-Dijen form, which is more deeper form, where all qubits are kind of described by Bogoliubov-Dijen in greater depth. And also it can be described by Ginzburg-Landau formalism. So today we will talk about Ginzburg-Landau and some practical aspects of this theory. All right, so so here is again just to memorize you the picture of hierarchy of theories. So the very simple is two-fluid model for coexistence of bosonic and fermionic liquid at the same time. So we have Fermi liquid of unpaired electrons, which produce dissipation, and liquid of bosons or quasi-bosons or Cooper pairs in a way. Then then there was a Bogoliubov-Dijon equations sketched, and now today we go with Ginzburg-Landau theory, which was actually given a Nobel Prize, was given to Abrikosov for discovery of Abrikosov vortex. And we are not going to touch other deeper theories like Gorkov propagators or Hubbard models or Ellsberg theory. That's a kind of purpose of future talk seminars, right? So here again, the same structure could be described by RCSJ model, by Bogoliubov-Dijon equations, or by Ginzburg-Landau. In my PhD, I have developed description of this structure, which is sketched over here. So I have used extended Ginzburg-Landau formalism, where various order parameters were present. So in particular, in the structure here, where ferromagnetic strip was evaporated on the top of superconducting strip, you could experience S wave, superconducting order parameter, P wave, and also triplet phase, and various magnetizations, directions, and so on. So the system could have like 10 order parameters at the same time. And this was highly nonlinear system, which could be expressed by coupled ordinary differential, nonlinear differential equations, partial differential equations. Yeah. Today we will rather go into one-dimensional case. So these things could become simpler. So this particular, let's say, feature of Andrew reflection, which is reflection when the hole goes into boundary between non-superconductor, superconductor, it can be reflected as electron. So in a sense, it's like particle is changed into antiparticle. But in both cases, let's say we have preservation of momentum, because moving electron from left to right it has the same momentum, or supposed to have the same momentum as moving hole from right to left. This is very particular Feynman interpretation of antiparticles as particles moving with reverse time direction. So like that's yeah. So this Ginzburg-Landau formalism will not particularly address this phenomena. Nevertheless, in Bogoliubov-Dijon equations, we have the case of self-consistency relation, which is very nasty relation, and so from certain point of view, we could use order parameter from Ginzburg-Landau theory and plug it into Bogoliubov-Dijon equations. It's a matter of some exercise. Yes, Łukasz, please go with your question.
Yes, I have such question. Maybe naive, however, please forgive me if so. Namely, what about the Cooper pair? Yes. My question is as follows. Cooper pairs can be created in specific conditions, in specific situation. And what about the strength of the attraction between the electrons creating Cooper pair? As I understand, this attraction is only equal to the with respect to the value to the repulsion, yes, between the electrons, because they have the same electric charge, repulsion, electrostatic repulsion. So what is the nature of the interaction between two electrons creating Cooper pair? I remember, but I'm not specialist on solid state physics, that there is an interaction between electrons and the crystal net. Yes. However, please, because you are a specialist, on solid state physics. So my question is caused by this topic, by this issue.
All right, thanks for your question. So essentially, in standard BCS theory, in theory of low temperature superconductors, which is about relatively simple structures like PB, like niobium nitride, NBN, and so on. We have pairing mechanism which is well understood. So pairing mechanism between electrons is due to electron phonon interaction. So the electrons moving in interspace between atoms, they feel the positively charged cores of atoms. So and then effectively they attracted to the cores. So in a sense, it's like they are like attraction from both sides. Imagine you have slightly positively charged cores and moving electrons in between. So effectively, this could be seen from far distance as attraction between electrons. So electron phonon interaction produces effective attraction between electrons. However, and this electron phonon interaction can be mediated by long distances, like 3000 angstrom, which is 300 nanometers, let's say. And so they feel attraction at very far distance, but when they come closer and closer, they start to feel that they have the same charge. So they have repulsion. So that's why basically the sea of Cooper pairs, this is like first stage of Bose-Einstein condensation, which is not fully taking place because at short distances there is repulsion that prevents from this full Bose-Einstein transition to take place. But still, so that's why the Cooper pairs are called quasi-bosons, because they have this feature that are not fully bosons. But that's how it's explained. So this pairing mechanism, yeah, there are some very specialists like Professor Józef Spałek from Jagiellonian University and many other scientists. They describe this pairing mechanism in greater detail, like with Hubbard's model and so on. But I mean, usually this is quite high electron phonon interaction strength. And electron phonon interaction is also proportional to resistance. So it turns out that superconductors, when they go out of superconducting state, are not the best conductors in a way. So that's what I can say in that regard.
Okay, so as a supplemental to my question, what about the distance between the electrons which create Cooper pair? As I understand, there is no necessity that these electrons have to be closely. Yes, the distance between these electrons has not to be very small. Yes.
Yes, that's exactly so.
Yes,
actually, the size of Cooper pair is measured by so-called superconducting coherence length. So this is the length after which the superconductivity decays. So if you have the grain of superconductor that is above superconducting coherence length, then superconductivity can last in such type of grain. However, if you take too small grain, this pairing between electrons will not be effective because the repulsion will be stronger. So superconductors have a certain limitation with respect to the size. So the size of superconductor cannot be smaller than superconducting coherence length. And typically for low temperature superconductors, it's like 100 to 300 nanometers. So they are exactly not that small. Formally, such distance is categorized as is a subject of interest of mesoscopic superconductivity. Mesoscopic structures is categorized as mesoscopic structures. So mesoscopic structures are a little bit above nanostructures. So in that sense, if you construct devices based upon using phenomena of superconductivity, then these devices cannot be too small. And indeed, Josephson junctions are not that small, and they are above 100 times bigger than the size of smallest transistor. So like transmon qubit has size of 1 micrometer by 1 micrometer essentially, and the size of today's transistor is like 10 nanometers could be. So you can put a lot of transistors across Josephson junction. So that's how it is. But still, the due to the fact there is no dissipation in superconductors, then it's worth of trying. It's worth of trying with implementation of electronics in it, and this is the case of IBM Quantum Experience. They have choose. That's why they choose superconducting phenomena as because it has macroscopic wave function present, which defends itself from external excitations, right? So that's how it is. Was my answer satisfactory to you?
Yes, thank you very much.
Okay, thank you. All right, so we have this Andrew reflection, and this Andrew reflection and this Andrew bound state is very important for description of Josephson effect in particular. So we will try to attempt in describing this this Andrew bound state by well, it cannot be fully described by Ginzburg-Landau, but you can combine those two formalism for certain type of numerical model. All right, so let me move on. Yeah, so this is this famous triangle which you already know. So yes, we are going with a Josephson effect, and maybe in some time I will also single electron transistor effect described in proximity to a superconductor. So this Ginzburg-Landau theory, which is going to be described today, is very much similar in mathematical structure to Rospitaevsky equation, which describes Bose-Einstein condensation. And actually in both systems you can have Josephson junction, Josephson effect, Josephson coupling, and Josephson junction in a way. But it's more practical to have Josephson junction in superconductors than in superfluids. So I will just skip more detailed description of Josephson junction in superfluid. All right. So as in regard to these two regimes of superconductivity. So two types of Josephson junction. So on the left side we have a tunneling Josephson junction. On the right side we have weakling or a constriction. So yes, this IV characteristic in both cases could be described by Ginzburg-Landau equation, especially I would say right side. All right, so let me dive deeper into this topic. But yes, so last week we have shortly mentioned about pairing. So I'm not going to describe right today pairing mechanism between two electrons, so two body system. And then there was a formula for this pairing was described by equation 4 for certain electrons of certain energy close to Fermi surface. And then there was a self-consistency equation derived as equation 5, which describes the delta is here the superconducting order parameter or the square root of Cooper pair density. All right, and then this was this BCS theory, which which I have described last time. I'm not going to go into that deeply. I will maybe mention that Ginzburg-Landau theory could be derived from BCS theory. And this was done by Gorkov. There was a debate whether, because like Ginzburg-Landau theory was known before BCS theory, and there was debate whether one's supposed to give him a Nobel Prize. But actually, so there are two ways of describing derivation of Ginzburg-Landau theory. One way is by thermodynamical assumptions, and second, or phenomenology, and second is by microscopic picture. And Gorkov gave this microscopic picture. It's in a Fetter-Walecka book. I'm not going to describe it right now. I'm just mentioning. So there's a mean field approximation which allows us to diagonalize these equations of motion, and then basing on that we obtain Bogoliubov-Dijen equations. All right, so yeah, let's move on. So this is mostly from Joseph Spike book on condensed matter physics, and here again there's this procedure of diagonalization, which I'm going to skip it because it's already published on the lecture on YouTube. Right. So then there is this is the end. We end up in equation 17 for effective Hamiltonian in BCS theory. And then there we are approaching this equation 20, Bogoliubov-Dijen equations. Un, Vn are wave functions of electron and hole. All right, so then now we need to go into simpler, and so that's highly nonlinear equation because order parameter depends is in the structure of the Hamiltonian. They're supposed to be conjugate over here. So if it's in a Hamiltonian structure, and so it like Hamiltonian eigenvalues depend on eigenvalues affect the Hamiltonian, as you can see. So yeah, it's so usually you need a couple of iterations to obtain self-consistency approach, but you can replace the self-consistency equation with Ginzburg-Landau equation with nonlinear Schrödinger equation. All right, so that's the end of BCS theory, and now we need to refresh the definition of functional derivative. I'm not going to dig into all theoretical aspects of functional derivative. This concept of functional derivative is applied to the case of functionals. So functionals essentially are different from functions, that the argument of function is like, let's say, scalar field or just real number or a complex value number. This is argument of function. The argument of functional is another function. So let's say, yeah, so there is shift of domain, and functionals are generalization of a function, and then you can have functionals of different type. For example, the integral from -infinity to +infinity modulus psi square, the x is a functional of psi, right? So that's how it is. And then the formula, the operational formula, is given by this 21 number, is denoted by 21 as the, and then what we have is f, and there is f function f of x plus epsilon Dirac delta x minus y minus f of x over epsilon. And here you just denote, please notice f of x and f of y. And there is characteristic small delta used to denote the functional derivative, while in standard function, the standard derivative, you have small d. And then there is also square, the habit of square brackets that is introduced explicitly to distinguish functional from function, because in case of function, we usually use rounded brackets, right? And then there is a variational approach towards derivation equations of motion. Yeah, I see there is a, all right, okay. So, yes, so for example, you can say that configurations of electric charge is in such a way across the physical system in such a way that it minimizes energy of electromagnetic field in the whole space. That's this type of argument. All right, so okay, let me move on. So and now we need to apply this concept of functional to nonlinear Schrödinger theory in a way. So it's good to know before that how this functional concept can be used, for example, in regards to Schrödinger functional, for example. Okay, and imagine that you are given. Okay, let's at first we can forget about. At first we can forget about vector potential, but let's say you are given effective potential and you want to find the solution of Schrödinger equation. And it turns out that if you choose trial functions like your distributions of wave function, it turns out that your solution minimizes such type of function. So there's integral from minus infinity to plus infinity, and there is a Hamiltonian. So let's say you can have a family of trial functions that you try to fit or find by chance the solution, and then if you are closer to a solution, the smaller value it is. So it's good to know that your solution minimizes such Schrödinger functional. And actually, you can, in a sense, point out that your equations of motion are due to the fact that functional derivative of such functional with respect to wave function is set to 0. So equation 22 will generate you automatically the Schrödinger equation. You need to exercise it by your own using definition from the previous slide. Also, the functional derivative with respect to vector potential will generate you equation for probabilistic current density. Can you hear me?
Yeah, right now, yeah, it looked like you had some connection
Yes.
error.
Yes, I did. So we finished
I can
equation.
tell you that it was for around 30 seconds, something
Or,
like this.
all right, so did I discuss equation 22?
Yeah.
And now you can see my slides, right?
Yeah, right now, not yet.
Oops, okay. So, okay, I see. Can you see my slides?
It's, oh yeah.
All right. So you have equation 22. So you can say that functional derivative is nothing else as generator of equations of motion. So if given problem in let's say in physics or in the fields of dealing with applied technology can be expressed by minimization of functional, then equations of motion are in a sense obtained by this functional derivative. So what does it mean? That you can in a sense approach to certain solutions without solving equations explicitly, but with minimizing its functional, something like that. And this is also the problem of neural networks, is also in a way represented by functional, and your gradient method is doing nothing else as it minimizes in functional. There is famous paper, the universe neural network, and you can see how this learning of neural network is expressed by functional derivatives. Always neural network expresses integral differential equations and such type of functional. Anyway, I will continue. So this Schrödinger equation of motion is equivalent to formula 22, and current density, probabilistic current density, which is present in Schrödinger equation, is by equation 23. So we have those two equations and these two type of functionals. Actually, you can have more fields than this. You can have magnetization. This was the case of my PhD and so on. So anyway, so this is, you need to exercise yourself how to derive Schrödinger equation from Schrödinger functional. That's a kind of homework. Please go for it. All right, so let me continue further. So, okay, and one of this, how to say, this is quantization of magnetic flux is typical for superconductors, and this is captured by Ginzburg-Landau theory, and actually Abrikosov vortices were a kind of discovered by means of Ginzburg-Landau theory. Actually, Landau asked him to keep it unpublished for many years. He didn't like the solution somehow. Anyway, so this is phenomena of flux quantization, which can be captured by Lagrangian equations or Ginzburg-Landau theory. But anyway, after one rotation, we need to go to the same phase of wave function. So phase can change by multiplicity of 2pn, integer multiplicity of 2pn. All right. All right, and now we are approaching to this fear of phase transitions, and this just remind for some of you that are less familiar that we have canonical ensembles. We have a microcanonical ensembles, which are picturized quite nicely over here. I found it this picture from Wikipedia. I took this picture from Wikipedia, and then we have macrocanonical ensemble, NVE. We have canonical ensemble, where TVN, you can say, is constant. Then you have a grand canonical ensemble when mu Vt is constant, mu is chemical potential, and so on and so on. And for those different ensembles, in a way, you have like different effective Hamiltonians, you can say. So for the case of microcanonical ensemble, this is a physical system that is isolated from the whole world, so there is no exchange of heat. So that's why number of particles are preserved, volume is preserved, and energy is preserved. So that's just traditional Hamiltonian, which is energy, sum of kinetic and potential energy. That's a mechanical energy in a sense, right? Yeah. So then for next, so then we can describe so-called thermodynamical potential proper for given ensemble. I'm not going to go into that, but I would just mention that for the superconducting phenomena, we need to describe free energy. We have to use free energy concept, Helmholtz free energy concept, when we have free natural variables, T, V, N preserved. Yeah, and then, of course, when we try to deal with phase transitions, we use the concept of statistical physics, and then there's a concept of partition function. And here's a formal definition of partition function. Please note that for every ensemble, like microcanonical, subcanonical, and canonical, and so on, you can define slightly different form of partition function, but essentially this partition function will have effective Hamiltonian which sits over here. And then you have summation or integration over the whole phase space of possibilities. So in a sense, this partition function is capturing all statistical possibilities present in the system. And then the Helmholtz free energy is related to statistical partition function Z by this formula. And yeah, and then we have, yeah, and then we will minimize it. And then this, in this so-called Ginzburg-Landau theory, could be obtained. It's important to mention that this theory only works for temperatures close to critical temperature, Tc. So this theory does not give the most exact results for the region of very low temperatures, close to the 0 Kelvin, let's say. Nevertheless, well, people can, Bogov-Dijen theory does. The Ginzburg-Landau theory is only valid close to phase transition, which means close for temperatures close to Tc. All right, and I'm not going to dig into all details over here, but let's say this there's certain connection with thermodynamics. So this partition function is like some normalization factor. Yeah, you need to exercise this concept, to digest this concept deeper on your own. As you see, there is a different grand canonical partition function from canonical partition function and so on, but that's something that you can grasp on your own. All right, so, and then this we have Landau mean field theory. I'm not sure if this is fully visible. Yeah, okay, so let me move on. Yeah, so, oh, sorry, I'm just cannot see. Okay, I think it's better in that way. All right, so we parameterize partition function by Helmholtz free energy. But before that, we have this this connection of this summation on all expressed by that equation, and H is here effective Hamiltonian, which is specific for given given statistical ensemble, and then in our case the statistical ensemble will be canonical ensemble, and then we parameterize this function, so by f minus f over k times t, temperature. And there is so-called saddle point approximation, where we choose such f that it minimizes. Yeah, so you will see this procedure in a kind of more systematic way. Here, we have so-called Landau free energy density, and this is nothing else as f function, f or sometimes g, depends on the book. All right, so let me continue. Yes, and now we have this concept of Ginzburg-Landau theory. I took certain slides from MIT course on applied superconductivity, but so the essential is that you have some physical field which minimizes you this functional, and if you are close to critical temperature, then you can always, you know, that the size of order parameter is small. In our case, this order parameter will be density of Cooper pairs, or the superconducting order parameter in a way. So superconducting order parameter C is square root of density of Cooper pairs. So basically, we scale the theory close to phase transition in a way that NS and NS square. Since we know that the Cooper pair density is small, we can take only the first two terms of polynomial as valid. And then here is a difference between superconducting state and normal state. And basically, alpha and beta are certain parameters of Ginzburg-Landau theory, which are as they are. And beta has always, so basically, the physical field is supposed to minimize this difference. And in order to favor non-zero property of superconductivity, so the physical field needs to be promoted, and this is achieved that this difference is zero, is negative. So negative difference, it turns out that non-zero order parameter NS minimizes, and this is achieved here and here. And so that's why that's why this superconductivity is a stable phenomena. And so essentially we have this functional minimization. And in case of bulk superconductors, it turns out that there is this ratio that density of Cooper pairs is minus alpha over beta. It's given like here. It comes from this and this derivative. So this is the situation of Ginzburg-Landau equation for no gradients. So this is like bulk solution of bulk, or case of bulk uniform superconductor where there are no fields. So then there is such condition. It's already a hint that density of Cooper pair is minus alpha over beta. It will turn out later that you can consider beta as positive and alpha as negative if you deal with superconductors, and if you move from superconducting to superconductive case, then alpha changes signs from minus to plus. So negative alpha values are encoding superconducting feature, superconducting presence of superconducting of Cooper pairs. So later it will turn out that you can have this, let's say, encode the superconducting feature by alpha map, and then whenever you place superconducting area, then you assign negative values to alpha. I will later describe you some results of Master of Science thesis, one of my students on that topic. So essentially, you need to understand that you can destroy superconductivity by following physical factors. First factor is by temperature. So the second factor is by strong magnetic field. And then you can evaluate this value of magnetic field. You can refer to alpha and beta parameters, and here it's described by this relations, by those relations, and yeah. So basically, all physical, so magnetic field presence is trying to rotate the spins inside Cooper pairs into one direction. So that's why it destroys Cooper pairs. So effectively, presence of magnetic field, or vector potential more exactly, is heating up or increasing values of alpha field from negative to less negative or into positive. Yeah, so you will be able to trace it step by step on with some examples. I'm just now signalizing to you that that's the way it is. So yeah, so basically the alpha field can be scaled linearly when we are close to phase transition, close to, for temperatures below but still close to Tc. Phase transitions, such formula holds 1 minus T over Tc times some constant, and here you have density of Cooper pairs, and there is a critical field, and also you have the prescription for beta values. So you see beta is always positive here, so it's mu critical field to the square over GL. All right, so so that's the way to scale alpha and beta coefficients. There is also a feature of, how to say, the superconducting coherence length is also scaled from with temperature, and so 1 over square root 1 minus T over Tc, as you can see. Also, close to critical temperature, you can scale the density of Cooper pairs, 1 minus Tc times this factor, and also critical field. So the closer you are to phase transition, the more fluctuations takes place. Yeah, and so that's what you need to understand. So that there is, if you are coming closer to phase transition, what happens is that you have more and more presence of normal electron liquid, fermionic liquid, and less bosonic liquid. until the moment where bosonic liquid is only present locally and then vanishes completely. So you have simply close more and more resistance whenever you go to normal state. You can detect this via the different types of measurement techniques. Okay, and now let me talk about explicit structure of this Hamiltonian. In a way, it's effective Hamiltonian. This has similar form as in reference to Schrödinger equation. There will be certain differences. Okay, so first of all is that order parameter is, so macroscopic wave function is order parameter in the case of superconductor. And the order parameter is square root of density of Cooper pairs times e to the power theta. Theta is a phase factor. And then theory can be written by this equation, this over here. So it's alpha and beta. It's alpha and beta. And here you are dealing modulus psi square. So this is in a way like density of Cooper pair. And here is a quadrature, the density of Cooper pair to the power 2 over here. So this is also called psi theory from field theory perspective. And you have the third factor, which is given over here. So here is like this, those two elements constitute potential energy in a sense. Here's a kinetic energy of condensate, of Bose-Einstein condensate described by Ginzburg-Landau equation. And then you have energy of magnetic field, and so on. What's the difference from Schrödinger functional is that here is a potential, effective potential. Alpha is effective potential in the Schrödinger equation, and there is no beta. Beta is 0 in Schrödinger formalism. So those forms are different, but the rest is bit the same. And yeah, and of course this is integral over the whole space. So this functional needs to be minimized if you let's say are approaching this numerical solution of given problem. Yeah, so let us assume the simplest case. In the simplest case, it's no presence of magnetic field, so those two terms are set to 0. And there are no gradients, so also you can assume that there's no momentum. So in the simplest case, you have only those two terms, but then for the case of uniform superconductor, you have no dependence on position. So this is psi, constant psi square and psi 4. So to minimize it, it essentially has to postulate that the sum of two will be 0. So that's why you get the condition that square root of psi is minus alpha over beta. So the psi is square root of minus alpha over beta from such minimization. So this is the solution for so-called bulk. All right, so let me move on. So that's how we have, and then I'm now describing static time-independent Ginzburg-Landau equation, because you can have movement of vortex and you have time-dependent Ginzburg-Landau equation. All right. So in normal state, it's good to pronounce that psi is set to 0 or tends to be 0. So this term is free. Helmholtz free energy for normal state. Okay. So, but what accounts is a difference. So this, yeah. So, okay. So, okay, and then maybe a couple of more practical issues. So you have the probability current in Schrödinger equation, in Schrödinger formalism, and this is pretty much the same current in Ginzburg-Landau formalism. So the only difference between Schrödinger equation and Ginzburg-Landau equation is that in Schrödinger equation, the effective potential does not depend on the wave function; it's preimposed externally, fully externally. While in Ginzburg-Landau theory, the effective potential is a function of C. So this is like effective Hamiltonian is a function of wave function. That's a prominent feature, and this dependence is nonlinear. So Schrödinger equation is nonlinear equation. Ginzburg-Landau equation is nonlinear equation, and basically Ginzburg-Landau equation has only one solution. It's very important. It has one solution, while Schrödinger equation has infinite number of solutions. There is a kind of novel method and there is always easier to solve Schrödinger equation because it's eigenvalue problem, and it's easier than solving Ginzburg-Landau equation. Nevertheless, I would say that you can find some level of mapping between solutions of Schrödinger equation and Ginzburg-Landau equations. So actually, I have modified relaxation method, and in this modification, what I have pointed is that you can use trial function. So solving Ginzburg-Landau equations, you can find trial function from Schrödinger equation, and this trial function will be a ground state of Schrödinger equation, which is usually only one ground state, and that's the essence of hybrid Ginzburg-Landau Schrödinger equation relaxation method, which perhaps I will mention in some time. Okay, so here is this Ginzburg-Landau functional, and well, there are certain connections which needs to be established by you via certain calculations. So let's say C is square of superconducting coherence length. So superconducting coherence is minus h bar square over 2m times alpha. Maybe one more thing. In Schrödinger equation, there is double multiplicity of electron because you have mass. So this is mass of Cooper pair, effective mass, and then there is effective electron of charge of Cooper pair is double electric charge. Just you need to recognize that, right? Okay, and then it's perhaps good to find some basic solutions of Ginzburg-Landau equation. Okay, so essentially the equation to remember is written by, in the middle of this picture, is given in the middle of this picture. So it's alpha C. So this is like alpha is like effective potential exactly, plus beta. So there is this nonlinear part of effective potential, beta times C square. So you have to understand that that's and plus just a kind of square of canonical momentum, this momentum, and there is a vector potential occurring also in Schrödinger equation. So you have standard derivation h over I d over dx, for example, minus this effective charge of Cooper pair. There is 2 times electron charge times vector potential. Yeah, so this is time-independent Ginzburg-Landau equation. And you can also have its time-dependent form, which I'm going to skip it now, but I believe this will be this form will be later tackled. So there is derivative with respect to time on the right side, and then some coefficient. All right, and like vortex flow could be described by time-dependent Ginzburg-Landau equation. Then there is a current density, that's equation below. And this is pretty much probabilistic current density taken from, this is the same, identical as in Schrödinger equation. There's different effective charge and mass is different, but the rest is quite identical. Mathematically, it's identical structure, actually. So you need to understand there are certain analogies between Schrödinger equation and nonlinear Schrödinger equation, that is Ginzburg-Landau formalism. And also this Ginzburg-Landau formalism is very much similar or near to Gross-Pitayevsky formalism, which is valid for Bose-Einstein condensation and so on. All right, let me move on. Then that's what I have already pronounced. Okay, so we have this internal potential, and just for you to remember, so there is, in this form, this alpha coefficient has like effective energy and effective potential. So just for you to remember. And whenever you have the boundary between superconductor and non-superconductor, then there is variation of alpha field, and beta is usually kept constant all the time. The exact values of alpha and beta coefficients can be derived from microscopic picture from DCS theory, but that's not exactly the case of this lecture. It's a little bit too advanced at this stage. All right, and yeah, that's macroscopic quantum mechanics. So then the feature of superconducting, the levitation could be described by Ginzburg-Landau formalism, and perhaps we are going to do some example on that. And the remarkable feature is that your superconducting cable could be also described by this Ginzburg-Landau equation, and this equation is much easier solvable than this Bogdanovich theory. Okay, let me move on. I think this is something what you already know. All right, so I think those two equations are kind of, so we have mentioned that for the case of bulk, density of Cooper pairs is minus alpha over beta, and also the superconducting coherence length square is h square over 2m alpha. Since alpha has negative values, so there is a minus. And you can rewrite Ginzburg-Landau equation in such a form where you have superconducting coherence length. And then it's also interesting to see that for a weak field, this trying to enter the superconductor will do everything it can to define its ground state. And so this will tend to have this canonical momentum set to 0. That's quite interesting to observe for a small magnetic fields trying to enter the superconductor. And then there is a density of so in case of superconductor, the probability current meaning is the same as electric current, so it has the same formula. So here you have this formula, and here this is quantized flux is denoted by this symbol. Okay, and you see then this is F is renormalized macroscopic wave function by bulk density. So basically, you need to remember that Ginzburg-Landau equation is nothing else as nonlinear diffusion equation. So there is diffusion of Cooper pairs from superconducting to non-superconducting area, for example. Okay. So Schrödinger equation is also diffusion equation in imaginary time, but this is linear diffusion equation, and Ginzburg-Landau theory is nonlinear. Okay. And there are certain types of solutions you can obtain for uniform cable when there's a current flow. So you want a limit, you're supposed to obtain the London relation. This London relation, which says that current density is proportional to vector potential, is a consequence of pre-assumption that order parameter in superconductor is constant. So you can have such type of relation as you can exercise how to obtain London relation from Ginzburg-Landau theory. All right, so now it's time to take some specific examples, and also there is critical current which so if you send sufficiently big current by your superconducting sample or Josephson junction, you can break down the superconductivity, which you will see immediately in your IV current voltage characteristics. And then you have specific values of coherence, superconducting coherence, and magnetic field penetration depth. So there is specific. So basically, superconductor is diminishing magnetic field. Magnetic field can try to penetrate superconductor. Usually, it has an exponential decay. So magnetic field can only penetrate until certain depth, and there is a specific decay length of magnetic field. So so there are two numbers: superconducting Cooper pair size or superconducting coherence length. This is the same type of basic physical quantity. And second is depth of penetration of magnetic field into superconductor. So there is this lambda, and those two values could be related to the pairing current. So this is current, which breaks down minimal current density, which breaks down superconductor. So which turns superconductor into non-superconductor. Usually, when you do experiments, when you force sample to go out of superconductor, then suddenly the Cooper pairs turns into normal unpaired electrons, and then suddenly there's increase of heat release because the electrons has the momentum, and suddenly they start to feel resistance. So suddenly there's a heat release and present in the experiment. Okay, and then you can think how to describe the Josephson junction having the solutions by solutions of Ginzburg-Landau equation. There is the way to linearize Ginzburg-Landau equation if you drop this H3 term C square times psi. If psi is sufficiently small, you can think that this term is not non-important. And then basically, by linearizing this Ginzburg-Landau equation, you're supposed to obtain the same relation as from DC and AC Josephson current relations. Then the same Josephson-Curran relation is supposed to be obtained from Ginzburg-Landau theory. It's quite obvious. So that's a kind of homework to think about this in greater detail. So basically, this is Joseph's microbridge, which could be described by this equation, by Ginzburg-Landau equation. And so we have pre-assumed that there is a bulk solution on the left and right. And then we search for a solution of this in this area in between. Maybe I will go for certain examples in some time. Okay, and it turns out that these solutions are like this. So we can pre-assume if you linearize, so if you have linear differential equations, superposition principle takes place. But if there's no linearity, you cannot do superposition. So then you can pre-assume that in the region over here, superconducting order parameter is weak, and then you can have superposition of two solutions. So actually, it could be diffusion of Cooper pairs from left to the center, and then diffusion of Cooper pairs from right to the center. So this could be expressed as the sum of two terms. So this is exactly this solution, which you can see here. And then, by proper calculations, you're supposed to obtain that the current flowing via this structure is sine of phase difference. So then you need to account for compatibility of two theories at the same time. So you're supposed to obtain the same type of results as from RCSG model. So actually, this Ginzburg-Landau theory is supposed to be a correction to RCSG model. And well, in a way it is. And then the Boguyov-Dijon equation is supposed to be correction to Ginzburg-Landau and RCSG model. And in a way it is, but it's quite time-consuming in a way. All right, so and then when we come into this formalism, there is a difference between type 1 and type 2 superconductors. So every superconductor has a feature of defending its ground state from magnetic field. So there is this Meissner effect, or this canonical momentum tends to be zero. So when you place superconductor inside magnetic field, the first effect is at the close to the surface that there's screening currents induced, non-dissipative screening currents. So they try to compensate the magnetic field entering the superconductor. So in a sense, screening currents create counter currents that try to make zero effective magnetic field inside superconductor. But when you start to increase the value of field in which you place superconductor, value of magnetic field in which you place superconductor, then the screening currents can be not enough to, and then either part of superconductor will turn into, you expect that part of superconductor can become non-superconducting, and indeed this is the case. But the difference is that, so suppose you have this, let's say, thin superconducting material, you place it inside solenoid where there is high magnetic field. For one type superconductor, the very strong magnetic field will make effective size of superconducting area smaller and smaller, but still it will be compact. While for second type of superconductor, what will happen is that magnetic field will punch the superconductor locally. So local non-superconducting islands will appear. And these islands will be called vortices. So magnetic field will penetrate superconducting only in certain areas, and these vortices will have quasi-normal core, which means inside their center, superconducting order parameter will be 0, and it will be increasing when you move to the boundary of this vortex core. So this is type 2 superconductor, and difference is between one type and second type of superconductor is that for type 1, superconducting coherence length, so the size of Cooper pair is bigger than decay of than magnetic field penetration depth denoted by lambda, while for type 2 superconductors, its superconducting coherence length is smaller than, so the size of Cooper pair is smaller than the superconducting, the magnetic field penetration depth, lambda. So that's a difference. So that's a criteria for existence of vortices. So we can also say that vortices repel each other for type 2 superconductor. So the magnetic field is punched, but then there's a screening current around the core of each vortex, while all vortices merge into one for type 1. So we'll deal with that in greater detail. Okay. And now I would like to describe a little bit of relaxation method. So this is the algorithm for, let's say, solving this Ginzburg-Landau equation practically in a way. So the F was free energy functional, Helmholtz free energy. And with respect, so functional derivative with respect to X is like physical field, like psi or vector potential was set to 0. So this is generator of equations of motion in a way. So this formula gives you generator of equations of motion. But in this numerical method, which I'm using, is that we preassume that we make a guess of initial configurations of physical fields. And then having this guess, during the algorithm, the functional will minimize until it approaches its minima. So, so we have some intuition as about topology of solutions, so we can make an constructive the guess, let's say. So, so this is so what we are going to assume in our practical method is that this functional derivative is set to minus some coefficient times and the finite change of physical field with respect to finite time. And here the time will be our virtual time of simulation. So this is the essence of gradient method. So in practically way of saying, it will be described by equation 3. So here you have Ginzburg-Landau equation on the left side, and on the right side you have some coefficient times change of delta psi. So you can iterate. So this is prescription for the whole lattice. So you can compute this. So if you don't have the solutions of Ginzburg-Landau equation, this will not be set to 0, but this will be a kind of non-zero. So that's why you will have non-zero value over here. So it's a prescription how, and the same is with this is the left side will be current density. So if you have fixed finite time step delta t, you can multiply both sides, and then you have prescription how to change the physical field on each lattice in your simulation. And it's the same with vector potential. So in a way, this algorithm has very extremely simple structure. And it effectively works in one dimension, even if you make a stupid guess function. It works less well, but still quite well in 2 dimensions and so on. So in my case, this gas function was the solution of Schrödinger equation. So it was a relatively intelligent gas function, I would say. But well, so the strength of this method is that it's very universal. And then you can also interconnect this current density with other physical fields as by electric field and vector potentials, as you can see here. Yeah, it's a matter of exercise with this method. So basically, this method can solve you this equation, time-dependent Ginzburg-Landau equation in this form, in 1 dimension, 2 dimensions, 3 dimensions, and even more. It's generalization. Okay, and how it works in practical way. You are given the nanostructure, let's say in 2 dimensions. You know which parts are non-superconducting. Vacuum is non-superconducting, so you assign positive value to vacuum, and let's say of alpha coefficient. So you need to have alpha map, and then you will assign 0 value, let's say, to normal metal that is in contact with superconductor. So you encode superconducting, non-superconducting properties by alpha field. Then you keep beta field constant, and then you make initial guess. So you know that if you have superconducting normal metal, superconducting like Josephson junction, you know that you need to propose that superconducting parameters is maximum on the left and right side because there is superconductor. So you do some kind of guess like that. Then you put it as initial parameter, then you iterate, and you iterate a couple of thousand times, and you always monitor the functional free energy, whether it minimizes, and your error. Error could be seen even from the point of view that the error could be seen that if this equation is non-zero, that's this value of error, right? So you iterate it a couple of times, and you just got it solution. And there was a Bartosz Stojewski presentation also at Quantum Harvest Systems YouTube channel that describes this method in greater detail. And this could be for the case of non-zero vector potential or non-zero magnetization, and so on, so on. So that's how it is. And there are the steps, detailed steps given here. And here's the case. So if you have alpha field like here, this is like negative. So this is like superconductor, non-superconductor, let's say, structure. So this is one-dimensional structure. And then you make initial, even stupid guess. No, this exponential decay. You expect a kind of exponential decay for the parameter. Sorry, I'm just need to see things. Initial. If it's, does it make? Okay, so I see. So I have two. Okay, so I choose 2 types of trial functions here, the blue and orange. And both, even stupid trial function gave one proper solution, which was as final. So pretty much the same solution was. So this method is even partly resistive towards silly gas function, let's say. This is one-dimensional case. And then during the simulation, there was a free energy minimized. That's supposed to be. The function that was minimized to negative values. And then there was a relative error that was not normalized. It's supposed to be normalized by the size of lattice. Anyway, it's a way to get the solutions in 1 dimension, 2 dimensions, 3 dimensions. And it's also nice of variational algorithm that I believe is supposed to be broadly developed. This broadly applied in educational methods, this relaxation algorithm. Yeah, so I used some materials from University of Cambridge, from MIT, from Spike book, and also superconductivity of metals and alloys and magnetism. I'm not sure what this. So I would like to, so please point me some questions or comments. Do we have more questions or comments? Wojtek, do you have any?
For now, I don't think so.
Eric, any questions or comments?
No, thank you for your lecture.
All right, so I will go for more, let's say, explicit cases of solutions of Ginzburg-Landau equation, analytical, on next lecture. So I would say just we need to address very particular structures of solutions, so to be able to handle this theory with certain skill, because it's necessary to know some basic solutions. And yeah. All right, so I guess we have a couple of more lectures, but basically that's okay. So do we have, and there's some comment I need to see. All right. Okay, so let's say, I guess that's all, guys. So see you next time. Thank you.
Thank you.